All right. So last section. Today we're just gonna go over the homework a little bit, and then talk about as we go along. Just talk about some ideas that we brought up probably multiple times over the course of the semester to just sort of keep in mind when trying to do these things in STAN. So the first question was about this multiple imputation algorithm for time series cross section data that's implemented in Amelia. This is essentially the only thing out there currently for dealing with data that are, why does it keep deactivating me? Dealing with data that are not simple random sampling. And in a manner of speaking, that is one of the reasons to account for its popularity in political science, particularly, but in some other disciplines as well. A lot of the other procedures out there, the stuff that's implemented in Stata and SAS and stuff like that, are really not appropriate for these time series cross section data because they assume just simple random sampling, and that's the only thing that you really have to take into account is the dependence across the variables. But that in the time series cross section context, there's a lot more dimensions of dependence that kind of need to think about. So the King and Honecker and King paper utilizes this M matrix, which is just 1 minus R as we've usually defined it. So R is 1 if the data point is observed and 0 if it's missing. Consequently, M is 1 if the data point is missing and 0 if it's observed. And all this multivariate normal stuff, assuming the complete data likelihood is multivariate normal with these multivariate normal parameters mu and sigma, and that seems right off the bat to not make a whole lot of sense, that it's ignoring the dependence over time within units in a time series cross section context. But this procedure allows you to have some basically derived extra variables included in the X matrix, which could be the lags of some variables. You can even have the leads of variables, because this is not going to be interpreted substantively. So there's not any real particular problem with predicting the past from the future. The X matrix can also have stuff that they talked about, polynomials of variables, so X and X squared and X cubed, stuff like that. And in particular, if you include a polynomial of order 0 with respect to time, and you can interact that with the unit indicators to put the basically dummy variables defining the units into the X matrix. And so although you can do that, these additional variables may put some serious strain on the assumption of multivariate normality. In particular, the unit-specific indicators are obviously dummy variables. If you include GDP to the 5th power or something like that, then that is unlikely to be a margin of a multivariate normal distribution. But there's nothing that stops you from putting these sorts of things in there. But that essentially is not too big of a deviation from what plain Amelia does. With plain Amelia, if you didn't have time series cross section data, you could still put squares and stuff of variables in there. It's, I guess, worth mentioning that, if you include the square or something of a variable, the imputations of that don't necessarily come out perfectly coherent. So let's say you're missing, GDP at time t, or really any variable, but you include GDP squared as one of the sort of auxiliary variables. And if GDP is missing at time t, then GDP squared is missing at time t. And a fully principled imputation algorithm would make it such that if you impute GDP, it's like $40,000 per capita, then squared GDP would be 40,000 squared per capita. But this algorithm doesn't really enforce that logical constraint. So really, it just sort of imputes GDP as a function of the things that are observed for that unit at that time, and then imputes GDP squared as if it were a completely different variable. So that is something to watch out for, but it's not thought to be a huge deal. Tara?
So I was talking about this imputation with somebody who will remain nameless, but you know who it is, who was very concerned about conditioning on only observed variables in doing this. So I guess my question is, like, I understand what their contention is, but how do you know what best to condition on? Just condition on everything that you have, or specify a theoretical model? I mean, the king and Hunter, they're just condition on whatever. Don't worry about causal stuff because it's not going to be causally identified in any way.
Yeah. Well, what most people recommend is to include at a minimum all the variables that are going to be part of the analysis model. And then secondarily, include any variables that are not going to be part of the analysis model that you think would be good at predicting one or more of the variables that is in the analysis model but has missingness on it. And then if you get outside Amelia to the point where you're modeling the missingness mechanism, then third, although not third in importance, but third, as I've already said, the first two variables that are good at predicting whether the value will be missing on one of the variables that is included in the analysis model. And then, from there, particularly in the time series cost, so that what I just said would apply even if you had simple random sampling or some experiment or something like that. And then in the time series cross section context, you have this additional stuff they say include the lag of important variables, and so you have to sort of decide which of the variables in your analysis model are important and which are unimportant. I would say probably everything should be considered important, but you can easily overstress this particular algorithm by going crazy with lags and leads of everything and squares and cubes of everything and interactions of all that with the dummy variables characterizing the cross-section units and all that. And we'll talk about that in a second when we get to the part of when this will work well, when it won't work well. So I would say the main innovation of this paper relative to previous papers by Gary and various co-authors about the multivariate normal imputation approach is that they come up with a scheme to allow priors on the missing values rather than explicitly putting priors on the common unknown parameters mu and sigma. And so this approach, I think, makes sense because if you could talk to an area expert or talk to someone in the government, presumably don't have a whole lot of knowledge about statistics or Bayesian statistics, multiple imputation, anything like that, it's quite likely that if you could find such a person, they would have an informative prior about the missing value at time t, because these units, oftentimes we're talking about a country in political science is a known entity. Whereas, for simple random sampling with a survey or something like that, the people are just going to be anonymous. And so unless you call like a psychic, they're not going to have an informative prior about someone whose, phone number got drawn with, randomly from a hat. I mean, maybe if you could find like a relative of that person or something like that. But if they're anonymized, then there's no real way you could express prior information on the missing values directly. But if we're talking about some country in sub-Saharan Africa that is usually going to have a lot of missing data, but there's people out there that you could talk to who would have probably informative priors. Now, this approach requires them to specify their priors in terms of marginal normal distributions. And so that can be a challenge. But this whole idea does go along with something that we've said probably 2 or 3 times previously, that insofar as you can give, set up your model to give opportunity for people who might be able to contribute prior information in terms that they understand. And so observables is probably, maybe the easiest. Location parameters after that. But if you start talking about like, skewness and things like that, then, the only people that could, help you are people who, really know a lot about statistics and happen to know the substantive area that you're talking about. And those people can be really hard to find. And so if we're putting priors on the missing values, like how does that exactly fit in to this posterior distribution? And this is where the paper gets a little bit harder to understand. You have to kind of dig through the appendix to figure out what's going on. But essentially, they're using a trick where the common parameters mu and sigma are one-to-one functions of regression coefficients and also the standard error of the regression. And so if you're going to regress like the jth variable on some other set of variables because you have missingness on the jth variable, then in principle there's some regression coefficients beta that correspond to that, which in theory can be represented by elements of the covariance matrix sigma. And the same thing for the error variance when predicting the jth variable. But if we also use the least squares representation of the linear model coefficients, then we can do it with observed data where the jth variable in X is basically taking the place of Y. And so if you have, normal prior beliefs about the elements of X, J that are missing, that is basically implicitly defining a normal prior on the regression coefficients. And if you have a prior distribution for the regression coefficients, then the mu and the sigma are deterministic functions of those things. And they talk a whole lot about the sweep operator, which was kind of beside the point for answering questions about the theory of this. But basically the sweep operator allows them to go back and forth between the regression representation of the dependence and the covariance and mean representation of the dependence. And so by going back and forth through those, they can get what arguably is a coherent posterior distribution to try to draw from. But in terms of Stan, it would basically be making the betas and the sigma and all that transform parameters, and the action is really on the unknown missing variables, and that's where they can state their prior information and then filter that through to the parameters of interest. But the other way in which this becomes a little bit tricky is that the posterior distribution that they're intending to draw from is basically a product of the likelihood for an individual observation, and the likelihood for an individual observation consists of information on all k of the variables. But what they're essentially doing is integrating out the missing data from the likelihood in order to get an integrated posterior distribution for mu and sigma, depending only on the observed data. So they put prior information on the missing values, calculate all this relationship between that prior information and the common parameters mu and sigma, and then integrate out the missing values. And this hinges on both of them, the likelihood and the priors being from a normal distribution, so that they're conjugate. And then when you get this, likelihood and posterior distribution integrating out the missing values, then once you have draws from that posterior distribution, you can use your draws of mu and sigma and the observed data to then get draws of the missing values, where the missing values are now basically the posterior predictive distribution of the posterior distribution that integrated out the missing values. So, when you do it in stand, you might, keep the missing values in, and you're pretty much just drawing from the posterior distribution of the missing values. But if you integrate the missing values out and then draw from them, then it's technically posterior predictive. But in any event, the posterior predictive distribution for the missing values that they're drawing from is, again, just going to be a conditional multivariate normal, conditioning on the observations that are available for that unit and the draws of the parameters that they get. And so they also don't do MCMC. Instead, they do a maximization procedure known as EM to get basically point estimates of mu and sigma, but they do bootstrapping of units in order to get some uncertainty about the draws of mu and sigma, and to carry that through to the imputations. Again, that is more of an implementation detail than really what the question was asking. And the answer to what the question is asking is basically this normal likelihood, normal priors on the missing values integrated over the missing values to get something in terms of the observed data only. So any questions about the first part of question one? You? Okay. So let me flip over to the rest of this. So there's probably a number of issues that you could think about as to when this is going to work well, in which cases this is not going to work so well. I mean, all the things that you would worry about doing multivariate normal imputation in the case of simple random sampling would continue to be the case here, namely that the data or the variables aren't multivariate normal, or the missing at random assumption doesn't hold, those sorts of things. But we've already done some homework problems where we try to relax that a bit, and certainly you can model the missingness mechanism pretty straightforwardly in stand. So in terms of things that are particular to doing multiple imputation in the time series cross-section context, I think one of the big ones that they didn't so much address in the paper is you actually have to have some prior information from, someone who's arguably an expert in the country. But by default, Amelia doesn't, the sort of default arguments to Amelia are not to include any prior information about the missing values. And because the way they've constructed it, there's not an opportunity to put prior information on the parameters themselves. You can't do like a weekly informative prior on the betas or anything like that would give it stability. So if you just sort of run it, but with the default arguments, maybe specifying the country ID and the time ID, then you're not really utilizing any prior information. You're just using the likelihood, and it's quite possible that you would get imputations that are just have huge variance or otherwise way off because you don't have any prior information to really anchor that. Ben.
So it seems like the paper was outlining the use of prior information on individual observations as a valid method. I'm sort of interested in where the acceptable boundary is between, putting some information on there such that you're not imputing stuff that's like just a comically inaccurate range versus like just over specifying the variables. And like at some point you go too far and you're just putting in the values rather than using like any sort of real imputation, right?
So if the expert is certain but wrong, then it's going to adversely affect your imputations. I think most of the time they wouldn't, hopefully wouldn't express complete certainty about the missing values. But I think in that case, and they don't really talk about it so much in this paper, but it's actually possible to do in Amelia already. And the McElreath book talks a little bit about that, is to basically, if you have a situation like that where someone says, I'm really sure about this, that might be a situation in which you might want to incorporate measurement error into the model if you hadn't already. And we haven't had really a chance to talk about that. But just, briefly, it basically says you have a latent variable for everything, or at least a latent variable for everything that you think is subject to measurement error, not like it's the country and island or something like that. I mean, you should know that definitely. But, for these things that even in the United States are not measured, super precisely, like GDP and stuff like that, to say, okay, there's a latent for true GDP, and then the observed GDP has some measurement error relative to that. And, we estimate a model with a bunch of latent values in it. And so that might be something that you would want to incorporate into an imputation algorithm anyway. So even if your data is not missing, it may very well be not correct. So a model for the underlying things could be useful there. But it might be especially useful if you think you have a way overconfident expert. Of course, you could just say like, just double whatever their prior variance is, anyway. But one way or another, you can avoid having deterministic imputations. I think the greater problem in practice is people, running, they're not themselves actually experts on any of these countries. They don't themselves bother to talk to anyone. They just sort of run Amelia with the default arguments, not putting any prior information. And, we've seen a few instances where if the criteria you're evaluating is predictive accuracy, and that's basically what imputation is about, predicting the missing values, then it's easy to do a lot better if you have some prior information than if you have no prior information. But people who either lack prior information or just don't want to put prior information to the imputation process because they think if they do, that will make it Bayesian, are probably getting some pretty ridiculous completed data sets. So the second piece is that I think you really need to worry about with an algorithm like this is, are the units having a homogeneous data generating process? And so to some extent, you can get at this a very little bit with the option that sort of interacts the time polynomials with the dummy variables for the cross-section units. But if you don't specify that, or even if you do, underlying this, you have basically common mu, common sigma, common betas for all the cross-sectional units. And that is something that is probably at odds with what your analysis model is going to be about. I mean, certainly, when comparative politics started going in the direction of more quantitative approach, there was models where you basically assume parameters that are constant across countries, even though non-quantitative comparative politics people thought that was silly. But even in the today, where you'll see more quantitative models allowing for country heterogeneity in the data generating process, we don't see that very much in this algorithm to impute the missing values. And that is basically probably something that they could improve Amelia a little bit, but it's not the more you allow the means and the covariances and stuff to differ from one country to another, the more you need some good or at least plausible prior information to try to tie this down. And if people are not really going to put prior information, it could easily get a lot worse, even if in theory there's an opportunity to make the imputations better. And then the third thing is that this particular algorithm doesn't actually, as far as I can tell, take cross-unit dependence at time t into account. So, all the countries in the European Union experience some shock at time t, and, how does that cause, the errors in those variables to be correlated? There's a little bit in the sense that they mentioned that the expert could come up with a prior value for one of the missing values by imagining or thinking about actual countries that are similar that were observed at that particular time in order to come up with the prior mean for that. But then again, you have to actually have an expert that does so. And even still, that's a pretty limited form of thinking about the cross-sectional dependence. And so you have a data generating process where there really is a substantial amount of cross-sectional dependence, and you have a non-trivial amount of missing values, and you're imputing using a model which basically assumes there is no cross-sectional dependence, then your completed data sets are going to have, basically being a mixture of the observed data and the imputed data, less cross-unit dependence than probably the true data generating process has. And that can cause problems with your analysis model, particularly if your analysis model, the reason why you're doing it is to understand or otherwise model cross-sectional dependence across units. You're basically attenuating the thing that your analysis model is attempting to shed light upon. So, that can be problematic as well. I didn't put it up here because it's not particularly specific to time series cross-section, but if you have a unit for which, none of your data are observed for that, then it's not quite clear what is the conditional distribution being predicted from. And that can sometimes happen if a country is hit with a natural disaster or a war or something like that, and it basically doesn't have any data at all that year. Of course, that can come up with survey data as well when you have a longitudinal study and somebody drops out. But again, that typically would suggest not missing at random process, and you have to model the process by which people drop out. We usually don't have a model for whether a country is destroyed by an earthquake or something. Okay, so any questions about that or any other things that you thought of that would be problematic about using this for TSCS data? No?
Problems that are going to be inherent to whatever, right? So if you have you're missing a data point that jumps way out of trends, I mean, it seems like no matter what you do, it's going to be very hard to find something.
Yeah, I mean, usually if you have a situation where a country, comes under some stress and its values at time t are missing, but likely to be way different from the adjacent years, hopefully your area expert would recognize that. But yeah, basically, and we'll talk about this when we talk about the STAM model, you pretty much have to assume things mostly move smoothly over time. In which case you're gonna miss a bit when either the process by which things evolve smoothly over time breaks or spikes or whatever. But ostensibly the putting priors on the missing values could help with that. Question? Okay. So they remark that you could do this sort of thing with real MCMC as well. I kind of started from the presumption that you weren't really going to have area experts on all the countries for which you have missing data, which is, a lot of countries. And to, try to do imputation process with reasonable but not too dogmatic priors on the parameters to try to get at the three sources of dependence in a time series cross section. For a particular variable in a particular unit, you have dependence over time. Then you have, for a particular unit, you have dependence across the variables. And then at a particular time and for a particular variable, you have dependence across the units. So the first one is actually, I think, the easiest and probably the one that would be the least objectionable by various people who are suspicious of multiple imputation or Bayesian inference or whatever. If you just do like an AR1 or an AR2 model for each variable, if you just did that, it would probably be pretty good. So that is basically saying the best things to condition on if you're missing something at time t is what are the observed values in the adjacent period. I didn't write it down here, but if you just do an AR1 model, the full conditional distribution of the missing value is going to depend on one lag and one lead, because that variable appears for the linear predictor of the next one. So you can actually work out what the full conditional distribution is of a simple AR1 model with missing this. And I think, just doing that sort of corresponds to what people is a better version of what people would do if they, didn't do multiple imputation. And this literature, particularly if you go back a few years, you see all kinds of basically ad hoc things where they'll just do linear interpolation or something to come up with ways to fill in the missing values, and that's not going to get the uncertainty right. But if you do something along those lines and incorporate some uncertainty into the process, that is really going to get you 90% of the way there. And that, in a manner of speaking, is an advantage of time series cross-section data, that you basically have always a really good predictor of the missing values, where, if you're just doing like a survey experiment or whatever, and you maybe only have like 7 or 8 variables, it may be the case that you don't have anything that does a particularly good job of predicting missing values on one of the predictors or something like that. So I think just having a model for the time evolution of a variable, really would be almost adequate right there. Not entirely adequate, because even conditional on the lag value of the same variable, there probably is some dependence at time t for the other variables for that unit, but that dependence across other variables can be handled in basically the same way that we would do multivariate normal imputation if there were simple random sampling, just allowing the errors for those k variables to have a multivariate normal distribution with a dense covariance matrix instead of doing independent marginal normal distributions. That by itself wouldn't take into account the probably third order thing, which is, the GDP of 2 neighboring countries is probably going to have spatial dependence. And so, if they have some sort of economic crisis in one country, that will probably adversely affect the economic indicators for countries that have a linked economy with that country who fell into crisis. And that's something that in principle you could do with some sort of spatial weight matrix. I'll show you how I started to do that in Stan, consisting of simplex vectors. But and you could do some spatial thing for the means of each variables. You could do some spatial thing for the errors of each variable. And basically to simultaneously account for dependence across variables and dependence across units, you could use one of the Kronecker product things that we talked about a couple of weeks ago to basically combine a error covariance matrix and a spatial covariance matrix thing. So let's just look at some of the Stan code for that. Obviously, you could do a lot of different things here. I have copied my function for doing Kronecker product in the functions block. And, depending on how you model things, this may be a little bit different. Assuming that all your units are observed for the same number of time periods, it could be advantageous to make R a three-dimensional array. So depending on how you set it up, you could order the indices different. But basically, here we have time periods, and those are basically going to be assumed to be conditionally independent with the autoregressive process. And then for each time period, we have what amounts to a matrix of the unit, the units and the k variables for each of those units at a particular time. And so we'll use R to remember which observations are missing and which are observed. As usual, you need to pass in the observed data. And this is a hyperparameter that I'm going to use for these Dirichlet distributions when I get to the weight matrix. So we'll get back to that. In terms of the parameters, I've basically put here that we're going to have an AR1 model, and there's going to be an AR1 coefficient row that's different for every unit and for every variable. But, whenever you add flexibility, you always want to take away part of that flexibility by shrinking it towards some global. So basically we have an unknown mean for those rows that vary by country and by variable, and also what do you call it? Not concentration parameter, but the other parameter in the beta distribution when you parameterize it in terms of a mean and a sample size rather than two shape parameters. So we're going to shrink all these country-specific, variable-specific rows toward a common value to keep it from getting too crazy. Then we're going to have a basically implied covariance matrix across the variables. So a Cholesky factor of a correlation matrix and some standard deviations. Again, decomposing this so we can use easy priors for each of them. Aaron? It doesn't have to be the case. So theoretically, it could be between -1 to 1. For most things in like comparative political economy, and negative autocorrelation doesn't make sense substantively. That would entail like oscillation. So, there may be some things in physics where that makes sense, but we don't do that here. So. So that was a substantive restriction, and also a restriction to make it easy to go with a beta prior on the rows. There is a beta, you can generalize the beta distribution outside the 0-1 interval, but in any event, for better or worse, that's what I did. Covariance matrix over the variables. And then this stuff here is for the cross-section dependence. And so I'm going to, down below, make a weight matrix, one of those W matrices. And again, those are characterized as being square matrices that are units by units. And in each row of that weight matrix, the elements are non-negative and sum to 1. And along the diagonal of that, it has to be 0, so you're not giving weight to your own country for those observations. And so that is actually something that is much easier to do in Stan than anything else that I know of. We just declare a array of simplex vectors. The simplex vectors themselves are going to be units -1 because we know the diagonal element is going to be 0. And the number of simplex vectors in that array is equal to the number of cross-sectional units that we have. And this whole weight matrix, when we get to it below, is going to be scaled by kappa. That's a parameter that has to be between 0 and 1, or I guess it could be between -1 and 1. I think we called that rho when we did the part on spatial modeling, but because I already used rho for the autoregressive parameter, I'm just going to call this kappa. And then we have, means and error variances for each of the units, each of the variables. And we're going to have, for each of the units and each of the variables, initial period that's unknown. So that's something that's missing for everybody. It's the value of the variable in the time period before you started collecting data. And we'll use that as for the linear predictor on the for the autoregressive part on the first observation. And then basically you have missing data, however many missing values you have for the rest of your data set. Those are going to be estimated here as well. And so in terms of doing a model like this, we're basically going to create a complete data vector that is a row vector of at time t of all the variables in all the countries. So this row vector is of length k times units, and we're going to have a predictor of that. It's going to be based on a autoregressive process. We have our cross-country W matrix, or I minus that. Then we're going to have sigma, which is a covariance matrix of the errors that's going to be based on the Kronecker product. And we are going to do various things that are kind of similar to what we've seen before, but maybe a little bit different. So the first thing I do is build up the W matrix. This is actually going to be 1 minus the W matrix, and I actually should be multiplying by kappa here. So again, if you work it out, if you have a spatial error matrix that depends on W, if you can get the reduced form of that, that is going to depend on 1 minus W times kappa. And so basically to implement that, we just loop through the elements to the left of the diagonal and pluck out the corresponding simplex vector, scale it up, multiply by -1. On the diagonal would go 0 of the actual W matrix, but here I'm thinking 1 minus kappa times the W matrix. And then for the elements that are to the right of the diagonal, we just keep it going, but are doing V minus 1 in terms of pulling out the simplex vector. And so that creates a legitimate spatial error matrix. We can Kronecker product that spatial error matrix with a covariance matrix for the variables, and then we get something that's going to be k by units by k by units to use as a covariance matrix for all those errors, taking into account both spatial dependence and cross-variable dependence. The rest of this is just modeling the autoregressive thing over time. So dealing with the initial period and then dealing with the subsequent periods So you have to loop over time, over variables, and over units, whereas before we were just having to loop over observations and variables, but basically doing something similar depending on whether R is 1 or 0 to get the observed data or the missing data, and then also to construct the X hat that you're going to use in the likelihood for the data. This has this autoregressive process where you have a mean multiplied by 1 minus the autocorrelation plus the autocorrelation parameter multiplied by the lag value for that variable in that unit one time period before. Then basically you get in a situation where at time t, given the X hat business, you're assuming that the observations are conditionally independent over time due to the autoregressive business. And so now at each time period, you just have a big multivariate normal taking into account spatial weighting of variables and the errors across variables. To do a model like this, you're going to need to have some reasonable priors. And so here's what I was talking about before, basically shrinking all the rows toward a common mean, the usual stuff with the covariance matrix. And in particular, this is pretty important. You wouldn't want to try one of these estimate the spatial weight matrix with no prior information. And the usual prior information that you would have if you don't have any, real other prior information is to use a Dirichlet prior on these simplex things that puts most of the prior mass on either having like a near zero weight or relatively high weight, depending on how many cross-sectional units, what constitutes really high may differ, but basically a prior that puts a lot of mass on these two countries just don't have a whole lot of dependence with each other is probably the most reasonable way to go. Anna?
So is the covariance matrix is not less complex how come that we have the most non-complexity thing?
Oh, yeah, that's wrong. So it should just be multinomial. Okay, there were, a lot of different ways that you could go with that, but that is definitely one of them. Ben?
I'm not sure I saw, so did you need to specify kappa as having 0 to 1? It seemed like it was just used as a negative. I was wondering if there's some kind of...
Yeah, I'm pretty sure in the spatial dependence literature, they would always constrain kappa to be 0, between 0 and 1. Basically, kappa equals 0 corresponds to the case of no spatial dependence, and kappa equal 1 corresponds to a degenerate thing. So they might put like an informative prior where I didn't for that variable, but I think it does need to be the case that it has that range. Okay, so moving along a little bit quicker. For question 2, this question didn't actually make a whole lot of sense in some respects. And since this was actually an experiment, you could just apply pretty simple experimental methods to it. They didn't have a whole lot of non-compliance, and there wasn't, a concern about defiers or anything like that. So you certainly could have done more simple methods, but it presented the opportunity to think about, what would you do if this was like worse compliance or observational study, like how would we do propensity scores or something like that. So Um, one reason why you might want to use something like BART, even in a case where you have a pure experiment, instead of just doing a difference in means, by modeling the outcome, you can certainly get more precise estimates of whatever your quantity of interest is. And if you use the BART machine, you're still not making any, dogmatic assumptions about linearity or anything like that. You are assuming the errors are normally distributed, but that's pretty much the only cost you're incurring relative to just doing a differences in means. And also, you have a principled way of dealing with missing this on the covariates, which is often the case even in experiments. This doesn't allow you to do missing this on the outcome, which is also unfortunately a pretty common issue with experiments. But if you assume the outcome missing this is missing at random, then you don't really need to model that or to consider it. It's just sort of a lower sample size than what you would want. So you can run all that. You can then do counterfactual predictions, setting the, hypothetically the randomized variable equal to 0 for everybody, and then, switching some of them to 1, then just doing a difference in means in the prediction. At that point, you're basically doing the differences in means. You're just doing differences in means implied by a model, albeit a relatively flexible model compared to like a linear regression, and taking into account which the basic stuff for linear regression or generalized linear models, they can't deal with missing this at all on the covariates, and here we're allowing that to be part of the tree that they split into. So that was the part of this that may have made the most sense in terms of you might want to actually do that. This covariance importance test can take a while to run if you're just doing it with one core, although the BART machine does allow you to do multi-core stuff. I think this could have come out either way, depending on what your outcome that you were modeling was. Different people had different outcomes. So you may have gotten, a p-value that was real small here, or maybe not. Did anyone get a negative p-value? I don't know. So any questions about that one? Okay, question 3, this is where it started to not make sense because the compliance was basically too good. And if you predict whether someone actually participates in the program based on their treatment assignment, which was randomized, you get probabilities that are real close to 0 or real close to 1, basically getting separation there. And it was hard to create for some of these sub-intervals where you had similar probabilities but different realizations of whether they participated in the program. So if this were an observational study and you got basically these very disparate propensities, then the stratified estimator would basically not be particularly appropriate because you don't have any overlap. But in this case, you would know that the lack of separation is primarily driven by the treatment assignment, and the treatment assignment is uncorrelated with all the predictors and any unknown predictors. So you wouldn't have to worry about that, and basically don't need to do stratification to estimate what this was. Ben?
I was curious why you memory cache for speed, that's a thing you recommend modeling off most specifying?
If you do it with lots of cores, it can overwhelm the memory. You get like Java heap error. And so this makes it go slightly slower, but use a lot less memory. But it should result in draws from the same posterior distribution. And so you can do that for the different variables, get the predictions for the p-hats, but the p-hats are going to be very close to 0 or very close to 1. So I didn't even bother actually stratifying. But, assuming this were an observational study or, a situation where you have more non-compliance, then, the main reason why you might want to prefer something like this to like two-stage least squares is the relaxing of the linearity assumption. And, the two-stage least squares is not going to have a principled way of dealing with the missingness.
So I had sort of trouble wrapping my head around why we would ever want to do this. If we had so even if there was two-sided non-compliance and a lot more non-compliance, I mean, if we predict the probability of taking up the treatment with treatment assignment, and then we are only comparing within small strata of a similar probability of treatment uptake, aren't we always likely to compare people who either received the treatment, both of them, and one did out of chance take it up and the other didn't for some whatever kind of reason? So I mean, aren't we always likely, isn't it similar to sort of conditioning on treatment assignment so that we always compare most likely within the people who have received the treatment or within the people who have not received the treatment, in which case we would exactly compare the people that we do not want to compare?
So it's true that you probably wouldn't choose to do this if you had a real experiment.
Or a real instrument, either the same, right? Because then would like with a real instrument, you also want the compliance. And when you condition on the instrument, you can only compare within the ones. So I don't know if that makes myself clear, but with a dummy instrument, for example, you would also tend to compare the people within the 1 category and within the 0 category of the instrument, which is not what you want. You want to compare those that take up whatever they should take up when they are in 1 and do not take up when they are in 0, right? So I don't really understand the whole approach.
I think
in the case where you have an instrument, I mean, I see when you don't have an instrument, sure, but
yeah. I think this is going to take more than 5 minutes to work through. But I understand what you're saying, and maybe we can talk about it on Piazza because we also got to do the third question. Tara?
Similar to what Anna's saying, so what I gathered, so I had perfect separation between the two. And so I took 100 people on each side of the cutoff and just compared them. So basically what that's comparing is like people who are least likely to take it when assigned to the treatment to those who are in theory most likely to take it when not given. It's hard to see like the insides of what Bart is doing. So basically, if you just compare those, you're going to get like an attenuated, like a lower bound on a treatment, right?
Yeah, if you're anything that is not over the whole population is not strictly speaking estimating an ATE.
Well, no, I mean, it's a conditional treatment.
Yeah.
But what I'm saying is like by taking like if you have separation like this, if you only take these two, these people are the ones who were assigned treatment but are least likely to take it, where these are the ones who are not but will be most likely to take it. So basically by comparing those two, you're like, it's a very weird comparison, right? Because you would want to like do the tops and the bottoms sort of.
Yeah.
Does that make sense?
That makes sense.
Just a quick question about the events here. Is there a reason to have separate sets of covariates for the different things? I mean, we wouldn't really expect like being assigned to SSP or SFSP to impact the prevents. It doesn't.
Yeah, I was just changing the
Yeah, no, I know
the last
that's what you pulled out, but it seems like including it wouldn't really change the results much unless we think that there's some interact. I mean, I don't know. Like I wouldn't expect assignment to one treatment to affect.
right.
Actually read the paper, but so I don't know how.
Well, they didn't do preventive. They just did traditional econ two-stage least squares and stuff. Yeah. I think there was some Piazza about that, but yeah, for any of these, I don't think there's too much cost to including a variable that actually doesn't predict the treatment. Okay, so we have like now 2 minutes, which is not really enough time to talk about question 4, I did put some stand code up for that, which does the dividing the the variables and stuff. I didn't actually run it yet. My computer was tied up on this presentation thing, but I'll put it up later tonight. The one-ish thing that I wanted to raise with this is, so if you looked at the vignette or something with the likelihood, there's actually a correlation or a covariance matrix. And so the important thing about this Tobin model is considering the correlation between the errors in the selection part of the model, like are you a 0 or are you a 1, with the correlation, each of those, or the correlation of that selection process with the outcomes if you're in regime 1 or if you're in regime 2. And that's the thing that if those correlations are non-zero, you could get bias if you didn't estimate a selection model. But what is fascinating to me about this, and in terms of doing it with Bayesian techniques, is that there's this third correlation in the correlation matrix that doesn't enter the likelihood. That is the correlation in the errors between the two regimes. So are you in treatment or are you in control? And this, although it doesn't enter the likelihood, is something that I think in most situations, people would agree that this would have a pretty high positive correlation. So whether you're in their program where they pay you to get good grades, or whether you're not, whatever sort of unobserved things that go into the error term would presumably be the same, whether you're in the program or not in the program. So if you have some thing that keeps you from doing well in school, that would tend to be the case in both of those regimes. So although that correlation doesn't enter the likelihood, it would presumably be pretty positive in most situations. And given that correlation matrices have to be positive definite, if you have a set of beliefs that this third correlation, which doesn't enter the likelihood, has to be pretty close to 1, like let's say 0.75 on average or something like that, then with the positive definiteness constraint, that affects your prior beliefs about the two correlations that do enter the likelihood. They have a more limited range that those two correlations can be consistent with the positive definiteness constraint when you have one correlation that's so big. And so one of the main differences with the Bayesian approach to this versus a pure maximum likelihood is that in the Bayesian case, you really need to express your prior beliefs about all three of these correlations, even though only one of them enters the likelihood term. And so if you do something that puts a high prior on that third correlation, that is really actually additional information, and it's additional information on the hardest part of the model to estimate, which is this error term business. So anyway, I'll try to write some more about that idea, but it's really one of the things in which maximum likelihood and using the likelihood as part of a Bayesian approach really differ. Okay, out of time. I will post the link to this, and